Hello everyone, welcome to this Roundup. While we have made formidable advances in software and the power and promise of software that learn by example is immense, the challenge has been so far about lack of parallel evolution in computer hardware to enhance machine intelligence for the complex problems we want to solve for the future of humanity. Moreover, since the traditional general purpose computing chips haven't changed much over the years and efforts are towards developing systems on a chip, there is an intense ongoing research focused on redesigning more efficient, lower energy consuming microprocessor chips that mimics the human brain circuitry. This rapidly evolving neuromorphic chips and platform is exciting many as it would allow us to design systems on the evolving neuromorphic chips. As a result, the competition is heating up. To discuss one such innovation, SpiNNaker, that is making headlines in neuromorphic computing chip space further, I'm honored to welcome Professor Stephen Furber to this roundup. Professor Furber is the Eisel Professor of Computer Engineering at School of Computer Science at the University of Manchester, United Kingdom. Welcome, Professor Furber. We are honored to have you on this roundup.
Hello, pleased to be here.
Wonderful, Professor. So it seems that today's computing architecture is not effective for building systems on a chip. Now, as we know, traditional computing rests on the basic idea that there are two computing elements, a CPU and a memory. So how is neuromorphic computing throwing that out and starting from a completely different point on the computing architectural spectrum? And what does it mean for computational intelligence?
The basis of traditional computing has been using engines or computers, processors that do very simple things very fast indeed. And this creates an illusion of complex behavior. The brain, on the other hand, does very complex things rather slowly. And so the inspiration behind the work we're doing is to see if we can build machines that work in a manner that's more similar to the brain. I mean, we can't make a machine that works exactly like the brain because we still do not have anything close to a full understanding of how the brain works. But we do know a lot of the detail of the brain, and we can use that to inspire new architectures.
So when you talk about the brain, is that what we are talking, the human brain that we are trying to mimic on a chip?
Well, all brains have similarities, and in particular, mammalian brains are very similar apart from scale. So if you look at a mouse brain, it's very similar to a human brain, but 1,000 times smaller and simpler. So the sort of inspiration we're taking, you could take from pretty much any brain in the mammalian branch of evolution. Of course, the ultimate interest is in the human brain itself, but building a machine of the scale of the human brain is still a huge challenge because of the complexity of that system.
It is a huge challenge. I agree with you, but I see the trend that everybody is going towards trying to mimic the human brain and trying to create the similar neural network on a chip so that we can build a artificial brain, the semiconductor brain that everybody is so interested in. So to build this network, feed it data, and that data will change the network much in the same way that this new information changes the brain. So what it seems like is that the chip can learn and infer on its own without any influence or any sort of external update from the cloud or the source, and it does all while using the fewer resources than a general computing chip. That looks like the premise of where the neuromorphic computing is taking us. But my bigger question is that why are we trying to create a similar pattern like a human brain? Because that brings us so many complex computing challenges, not only computing challenges, but in my assessment, I see that the neural networks that we are trying to create on these chips, and we are trying to build autonomous systems based on that is the foundation of where we will see the strategic security risk emerging for the survival of the human civilization itself. But that is a topic of discussion for some other risk roundup. But what I would like to ask you is that we understandably, to execute these neuromorphic algorithms efficiently at the large scale requires new hardware and computing infrastructure capability. So it seems that many new prototypes of neuromorphic chip are coming to market, including yours that you have designed and developed, the SpiNNaker. So what is the current state of innovation in neuromorphic processes, and how do you see the neuromorphic chips evolving in the coming years?
Well, neuromorphic hardware has quite a long history already and can be traced back to the early work by Carver Mead at Caltech in the 1980s. And in the early days, there was an attempt to understand, if you like, the physics of the biological brain cell of the neuron and model that physics in electronic circuits, effectively building analog circuits that had dynamics very similar to brain cells. And there is still neuromorphic research that proceeds along those lines. Our colleagues within the EU Human Brain Project at Heidelberg are building analog circuits that have dynamics very like neurons, and they call that physical model neuromorphic computing. Our SpiNNaker machine is digital. Instead of modeling the equations in circuits, we implement them in software. This produces a fairly similar result. We can then use conventional processors in very large numbers. If you look at the current state of the art, then people are taking a range of approaches from Carver Mead's original sub-threshold analog circuits, which use extremely small currents to compute very like biological cells, through digital hardware, epitomized by the recently launched Intel Loihi chip, which is a fully digital system. And of course, IBM 10 years ago launched the True North, which is in a similar space, where the circuits that model the neurons are implemented in hardware, all the way across to chips such as SpiNNaker, where the algorithms are implemented in software. And what you see across this spectrum is a range of trade-offs in terms of energy efficiency, flexibility, and performance, and so on.
Yes, so as you just described, there are many developments happening, Intel and then IBM and then SpiNNaker and many others. That some of them are analog chips, some of them are digital, and there is some are emerging as hybrids. So as these neuromorphic chips will be designed to process sensory data such as images or sounds and to respond to changes in that data in real time in ways that they are not specifically programmed or trained for. How do you see that changing the machine intelligence or the deep intelligence going forward?
Well, of course, alongside the last 10 years of developments in neuromorphic technology, there's been this explosion in machine learning, AI techniques based on earlier forms of neural network, based on the multi-layer perceptrons from the 1980s, and developments of that have become very successful in machine learning applications. The neuromorphic approach is closer to biology, but much less well developed when it comes to finding applications. Our motivation for SpiNNaker was really to try and build a machine that would accelerate our understanding of the brain, rather than build a machine that would deliver applications to the customer. So there's a spectrum of approaches, and I sense that these two approaches have developed in parallel over the last decade, but there's now a kind of convergence that industrial machine learning has got so far, but now needs some new ideas. It also needs some new techniques for significantly improving energy efficiency, particularly in the training phase. And neuromorphic technology may offer some new approaches that will deliver those benefits. That's still to be proven. There's a lot of expectation and hope that we can demonstrate those kind of improvements, but the proof of the pudding is in the eating, as they say, and we have yet to deliver that proof.
Yes, no, I'm glad to hear about the point that you mentioned, that the focus is more on understanding the human brain. That is really, I'm really glad to hear about that, because if we are trying to apply the same phenomenon, the same foundation principle of the neuromorphic computing to other applications, to other autonomous systems. For example, lethal, autonomous systems, and in where the drones are, based on that, developed on that, or missiles or any other weapons are being developed using this kind of technology, then we are creating much bigger problems. But I'm glad to hear that your focus mainly is right now for the SpiNNaker focus is to understand human brain. That will give us a lot of insight into many problems that we want to solve for not only the human biology, mental health, but also for the future of humanity. But going back to this discussion, even if today's neuromorphic chips are nowhere near as capable as the human brain, do you think that they would be much faster, or would they be much faster than current computers at processing sensory data and learning from it?
It's still very difficult to build computer systems that learn online. So all the progress I described in machine learning is based on effectively two phases. There's a very compute-intensive training phase, and then there's a rather lower cost inference phase. But when the network is in service in inference, it's not learning. It's implementing what it learned in the training phase. There's a hope that by learning more from the brain, we can build systems that continue to learn when they're in service. This seems particularly important, for example, for autonomous cars, that they can learn from their mistakes and improve over time. But of course, if they're equivalent systems, then they can each learn from each other's mistakes, which humans are not very good at. We humans, we tend each to have to make our own mistakes before we learn properly. With machines, it's rather easier to transfer learning between them if they're using very similar hardware platforms.
Yes, but isn't it ironic that we humans, we don't learn from each other's mistakes? We have to go through that ourselves to learn that. But we are still developing the artificial intelligence, or this neuromorphic. We are trying to develop the brain, and we are hoping that for autonomous cars and all these new initiatives that are emerging, that they will learn from each other. And that's where the bigger security risk I see emerging, because we humans are not designed for certain things, and we are trying to design the systems that we are trying to develop based on human brain approach. And that's where a lot of security challenges are emerging, because if you see, the lot of people's goal is to develop artificial super intelligence with that has conscience and that has a mind of its own. Now, if you look at the scientific research, it says that the violence, as well as the this empathy and all that, is on the same neural network. So if we define the same neural network on these computers or on these chips, then we are replicating the challenges that humans have in a much bigger way. And when the nations start this building lethal weapons based on those chips, then we have no idea how these autonomous systems that we are trying to build are going to react, how they are going to decide their goals, their objectives, and when they would decide what needs to be done for the security of the autonomous machines or systems, or for the security of humanity. So a lot of security challenges I see emerging from this. But talking about this SpiNNaker, how are the neuromorphic chips that the SpiNNaker chips that you are developing, are they energy efficient, and how is the energy requirement for this?
The SpiNNaker chips have been optimized for energy efficiency. So the machine is based on a custom system on chip design, where each chip has 18 processors, and collectively those 18 processors with their memory use below 1 watt of power. But we have a large number of those chips, so the complete machine with 1 million processors can, in principle, consume up to 100 kilowatts. In practice, it rarely comes even close to that. in practice, the activity is distributed and stochastic, variable over time. So the average power is quite low. So the machine is built for efficiency. If you measure its efficiency in terms of standard computing terms of operations per watt, then it's fairly representative of today's mobile sort of energy efficient systems, the kind of efficiencies you'd find in a smartphone. It has extremely efficient communications throughout the machine because, in fact, if you look at the design of the machine, the compute problem is relatively straightforward. It's the communication problem that's a challenge, and that's where the major innovation is in SpiNNaker, is not in how we compute the models, but in how we communicate the spikes between the models.
Yes, yes, I hear you on that. So, do you, what temperature the SpiNNaker chips require for it to operate? Because it seems that there are, for efficient functioning or for the atomic structures of the conducting materials, it changes at specific temperatures, and that is perhaps a key requirement for efficient signal transmission in the neuromorphic chips. So, how does the SpiNNaker chips, work around that?
The SpiNNaker chips, they're built on a conventional CMOS technology, the same technology used to build chips in phones and so on. And it's a technology which is pretty flexible in terms of temperature. The design tools allow you to specify the operating temperature range and make sure that the design is suitably margined for all its operating conditions. Because SpiNNaker is a low power chip, we don't have to worry about it running too hot. And in fact, we package it with an industry standard DRAM chip. And that DRAM chip is much more temperature sensitive than the SpiNNaker chip. So it's really the memory chip that determines the maximum temperature, which is around 80 degrees C. And we try and control and cool the machine so that the silicon temperatures are generally well below 80, so around 50 or 60 degrees if the machine's very busy. And at that temperature, conventional CMOS is perfectly happy.
Oh, good, good. I'm glad to hear that. Now, shrinking down the power of a neural net onto a single semiconductor chip means that these learning and pattern recognition technologies we can embed into a wider range for building systems in future, like systems on chip. Now, what potential do you see the evolving broadly semiconductor chips or even the SpiNNaker chips for developing systems on a chip?
Well, you're quite right that these chips deliver novel learning capabilities. They're learning capabilities that we don't yet fully understand how to implement and how to use. On SpiNNaker, the learning algorithms are, again, just small pieces of software. So they're very flexible, they can be reconfigured, and we can experiment with them. But we don't yet, in the world of spiking neurons, have anything close to the learning power that's used in backpropagation in conventional neural networks. Backpropagation is a technique that goes back to the 1980s, if not before. It's a form of gradient descent learning, and it's become phenomenally effective over the last decade. And spiking neural networks are still playing catch up in that space. They have the potential for very different learning capabilities, but that potential is yet to be really proven in practice.
Yes, yes, definitely. This is still very early stages. Now, today's digital chips make computation based on binary on-off signaling. Now, neuromorphic chips work in an analog fashion, and they, like you were just talking, they exchange burst of electric signals at varying intensities, much like neurons in the brain. So, how is SpiNNaker developed, and how is the brain analysis that is trying to do or trying to understand the human brain? How is it trying to solve that problem?
In the brain, as you say, neurons communicate in real time predominantly by emitting spikes, which are pure impulses of energy. And the information they convey is entirely in the timing of the spike. So it's the neuron that spikes and when it spikes. The shape of the spike itself carries very little or possibly no information. Because of the way it's propagated along the wires, there's a regeneration in those wires that sustains the signal. So even if it goes into the wire at a different shape, it will come out at pretty much the same shape every time. Now in SpiNNaker, we cannot implement the number of wires that you find in the brain. Wires in modern electronic technology are still quite expensive. What we can do is exploit the fact that electronic wires are much faster than biological wires to effectively send many different spike signals down the same set of wires. And in SpiNNaker, we do this by turning every spike into a little packet, and then we convey these packets over a packet switch fabric. Packet switch fabric is something like the internet, where you get a little unit of information that flows around and is routed at various points to its final destinations. And on SpiNNaker, each spike becomes a packet, and the goal of the machine is to deliver all of those packets to all of their destinations in biological real time. So we don't literally implement the spikes as electrochemical impulses. We implement them as packets. And the abstraction, if you like, the way to think about this is that the brain is effectively an event-driven computing system. A neuron spikes, that's an event. In SpiNNaker, the event is represented differently, but it conveys the same information to the same places. The information it conveys is that this neuron has just fired. How you do that at this level of abstraction doesn't matter in practice.
Yes, yes, that is true. Now, where do you see SpiNNaker going? What is the potential?
Well, the major feature of the machine is its scale. Because of the innovation in the communication system in the machine, we have scaled it up to 1 million processors. That's not a fundamental limit, it's a practical limit and a financially determined limit. We're an academic research group, so our budgets are small and finite. What we really would like to do with that is demonstrate the kind of science that can be done at scale. My feeling when it comes to sort of understanding the brain from the outset of the project was that the action is really at the network level. So the very fine details of the neurons maybe aren't so significant. What's important is how millions of neurons interact, and hence the emphasis on scale. And on the current SpiNNaker machine with its 1 million processors, we can, in principle, for example, run a complete mouse brain model. Now, complete mouse brain models are just beginning to emerge in other parts of the Human Brain Project, but they're not in the form where we can easily map them onto SpiNNaker, but that's the kind of capability we have. We've run in the past small models of mammalian cortex, a model developed with our collaborators at Jülich in Germany, and we are now in the process of scaling those models up. The ones we ran originally were just used 1 or 2 SpiNNaker boards. We have 1,200 boards in the machine, so we can scale up by several orders of magnitude and explore what changes in neural networks when you make them really large.
Yes, yes. So, can you repeat that last part? I couldn't hear properly.
I say what we're trying to explore is the effective scale in neural networks. What is it that you can see if you model a really large network compared with the limited vision you get if you run the sort of small models that you can run on a conventional computer?
Yes, those are the questions we need to analyze, and those are the points we need to discuss, because as we see currently, when we look at the vision that a lot of visionaries have, is that we are trying to build a decentralized economy in the coming years, that everything will be decentralized. And then when we are trying to see where the computing environment is going, where the systems on chip and all the neuromorphic computing evolution is going, then we are seeing that all these efforts are towards building centralized uh, systems. So there is a clash I see there, that between the blockchain decentralized vision that a lot of visionaries have, and where the blockchain is future is moving, and where the future of the AI is moving. And I see both the futures should be integrated, because blockchain and AI needs to move together, parallel. And that means that the efforts that we are trying to make in developing neuromorphic computing chips, that they need to be such that we can also work in integration with the blockchain vision that the world has, and where the blockchain is moving. So that's why a lot of confusion is there, that I while there is a need for integration between blockchain and AI, and blockchain could be powering the AI needs for tomorrow, as we try to as the efforts are more towards developing artificial superintelligence, and there is going to be huge energy requirement for that. There is a school of thought that it's the blockchain chips that would be perhaps powering the needs, or providing the energy needs of the art, developing the artificial superintelligence. But I see that all these developments are happening in silos, and there is no integrated vision between blockchain and AI, and there needs to be, because both the developments needs to happen in parallel simultaneously. But as far as talking about the design requirements for SpiNNaker, what is at the center of uh, trying to make the SpiNNaker more mobile and more, efficient?
Well, if one wants to build useful networks on physically smaller SpiNNaker systems, then of course we have to exploit higher integration density. And the current SpiNNaker machine was fabricated on a fairly old technology, so there's certainly an order of magnitude improvement in density we can get just by using a more modern CMOS process technology, and that's what we're developing for the second generation machine. And that would allow us to put a network of the scale of an insect brain into a 1-watt chip that you could potentially mount in a small drone. So, an insect brain can control a flying insect. Maybe it can control a small drone, if we can understand how to get the two things to interact. I think you talk about artificial superintelligence. I think that is a very long way off at the moment. We are not even close to being able to model the intelligence of a honeybee, let alone a mouse. I also have this sort of philosophical feeling that we don't understand what we mean when we say superintelligence. We think, I'm aware of the theory of the singularity in intelligence, but I'm afraid I'm a bit skeptical about these theories. I observe that human intelligence has multiple dimensions. It's not a single parameter that can easily amplify itself. There are many dimensions to human intelligence, and it's a very complex concept. And I can't conceive what a higher intelligence than a human, what properties it would have. But it feels to me it's still sufficiently far off that I'm not going to meet one in my lifetime, and I suspect many generations after me will be able to say the same. And because this is a research area, of course, research has to be focused. We in academia we operate research on quite restricted budgets, and therefore we cannot solve all the world's problems at the same time. We have to focus on a particular challenge,
Yes,
and see if we can address that with the resources that are available to us. We do have to increasingly think about the wider ethical implications of the work we do. So certainly, you mentioned autonomous weapons earlier, and there's a very strong movement to consider the ethics and effectively try and achieve international agreements on the regulation and control of autonomous weapons. Although I would note, of course, that there has been an autonomous weapon around for a very long time. It's also been banned, and that's the anti-personnel mine. That's a device which, in a very simple way, decides when it's going to go off and who its target will be. So this isn't a new problem, it's just that we have more sophisticated technologies available now to build autonomous weapon systems. But we also have very major issues with diseases of the brain, that the large pharma companies have largely stopped investing in drug development for diseases of the brain because they don't have the functional models. The way they develop drugs is to understand the disease pathway and then design the drug to interrupt that pathway. And in the cases of diseases of the brain, we don't have the models that tell us what the pathway should be. So there are clearly risks in developing more intelligent machines, but there are also potentially huge benefits in increasing our understanding of the brain. And these have to be held in balance in some appropriate way.
Yes, absolutely. Now I hear you on that. There is mental health is a huge challenge, and so are many other diseases. So if we are able to, if this kind of progress in computing is going to enable understanding, it gives us an ability to understand these at a deeper level and helps us solve the problems. Then we have to move forward, and at the same time, we are not never going to stop progress and development. But we do need to be mindful about where are the security risks going to emerge. More than ethics, I'm more concerned about the security risk for the human civilization, that while we are making an effort to develop all this intelligence that could perhaps be much more intelligent than human species, then there is a security risk emerging from that, because we will just be another species, and they may, this debate is already ongoing, that they may not find us necessary. They may find that human species are irrelevant, and there are a lot of security risk emerges from that. But there are, before we reach that point, there are many other security risks emerging. But let's talk about the SpiNNaker. That it is certainly a novel chip, and it has a huge potential. It's based on this ARM processor, which is designed to support large-scale spiking neural network simulation. So what allows SpiNNaker chips to be connected together to form scalable systems?
The scalability is based on the innovation in the communications infrastructure that we've built, and it's quite straightforward to describe. In the brain, the neurons are very highly connected. So a typical cortical neuron connects to maybe 10,000 other neurons. In the cerebellum in the brain, there are neurons that have 250,000 inputs from other neurons. So the challenge is, when the neuron spikes, is to convey the information about that spike to thousands, tens of thousands, sometimes hundreds of thousands of destinations. And conventional computer communication systems are not very good at this. They're designed for carrying large amounts of data from point A to point B very quickly. But if you have to carry it from point A to point B, C, D, E, and F, and 1,000 other points, then it becomes much less efficient. So in SpiNNaker, the communication is fundamentally multicast. The thing that makes this possible, of course, is that in the brain, the neurons that a particular neuron projects its spikes to are pretty constant. They are static, or at most they change slowly. And therefore, the routing of that spike is something that can be pre-computed and held in hardware tables across the machine. So we exploit the fact that this multicast route that a packet takes is constant, or at most slowly changing, to implement a novel form of multicast communication that's very efficient. Each SpiNNaker chip has, as at its heart, a router, and these packets are passed from chip to chip, neighbor to neighbor, and each chip performs a routing operation, but it's extremely lightweight. So the packet can pass through 5 chips within a microsecond. And that means it can get across the million core machine in a very small fraction of a millisecond, which is the requirement for biological real time. So in the brain itself, long communication actually takes quite a long time. Signals take maybe 20 milliseconds to get from one side of your head to the other. In SpiNNaker, the machine is much bigger. It's in 10 data center style rack cabinets, but the signal can get from anywhere to anywhere in a few tens of microseconds. So effectively, we can abstract the topology of the hardware and implement any neural network topology and maintain biological real time, irrespective of its physical disposition in the machine.
Yes, yes. No, that's very interesting. So this neural network mapping that happens onto the system, what methods do you use for that, and how do you ensure that when the chip is delivered for whatever functionality or what the purpose that it needs to work on, that it will work as anticipated?
The mapping is a software function. It's carried out by a large stack of software that runs on a host. So there are 10 racks of SpiNNaker chips, and then there's another rack of conventional cluster type computing resources. And the cluster computing resources compute the allocation of populations of neurons to processor cores, and they compute the routing tables to make the necessary connections. So the user of SpiNNaker can describe their network in a high-level language. We currently support PINE, which simply stands for Python Neural Networks, and it's become a widely used standard way of describing spiking networks, at least across Europe. And our tools will take the PINE description and perform the allocation onto the machine and load the network into the machine. So it's quite a complex software task to get the mapping right. And it's a research tool, so it isn't perfected, and users have to be reasonably patient. If their first attempt to map their network, the network doesn't run as expected, then they have to understand what's going on a little bit better. And we have a help email alias, so that they will say, I tried this network and it didn't work, and then we can give them advice as to what they should try next. It is a research environment, not a commercial production environment, but the tools are quite powerful, and quite a lot of very complex networks now run without any difficulty.
Yes, no, you're right that it is a research environment and there is still a lot that needs to be figured out. So what do you think still needs to be figured out, like in terms of technical, non-technical challenges for SpiNNaker to be used or applied to develop, many different systems that could emerge from this?
There are many directions to the research at the moment. One of the clear directions is scaling up to larger networks to find interesting large networks that will test the full capabilities of the machine. But there's also at the low level, there's research into what's the right way to model a neuron. The very lowest level, how can you make the differential equation solvers more accurate in the environment they're running in, through to interest amongst computational neuroscientists in slightly richer models of neurons. So we tend to focus on the point neuron end, where most of the spatial distribution of the neuron is ignored and all the functionality is considered to be at one point in space. But there's growing evidence that pyramidal cells have at least 2 separate functional units that communicate and that need a slightly more sophisticated model to capture their important properties. So we're exploring many directions. Within the Human Brain Project, we have many collaborators who have a lot of knowledge that's relevant to guiding how we develop these models. So there's no shortage of interesting things to do. There's rather more a shortage of people and resources to follow all the things we'd like to.
Is it a global collaboration on this Human Brain Project, that everyone is working together trying to solve the problems?
Well, the Human Brain Project is an EU project. So it's funded through the European Commission. So the funded partners are primarily in Europe, although of course there are partners in the EU science programme who are outside the EU itself. And there are other countries that participate through their own funding schemes and are associated to the Human Brain Project. With SpiNNaker, we have users outside the HBP. We've been delivering boards to several places in the US have SpiNNaker systems now. And you can find SpiNNaker anywhere from North America to New Zealand. So there is a kind of global, small but global network of SpiNNaker users. And so that clearly goes outside the HBP. I mean, a lot of the major science countries now have their own brain programs. So there's a big brain program in the US. Of course, the US also has the Allen Brain Institute, which is a very major center for research in brain science, but there are brain programs in Japan, China, Australia, as well as the EU and North America. There's a Canadian one, I think, being announced recently. So there's a sense that the time is right for taking on the challenge of trying to understand more fundamentally how the brain works. And I think part of the reason the time is right is because of the growth in the capacity of computers. We can now conceive computers that are big enough and powerful enough to support whole human brain models. Nobody's built one yet, but they're probably only about one generation of high-performance computer away. They're within sight, and we can certainly build very complex models of major brain subsystems already. So, so I think there's a strong sense that the time is right to take this on, and the benefits that will come will be both in the direction of medicine and in the direction of AI, I suspect.
Yes, certainly their potential is huge. So what would you like to tell our global viewers and listeners about the potential of SpiNNaker, and where you would like to see the applications emerging from across nations that they can use SpiNNaker?
Well, I think SpiNNaker occupies a particular niche in the space of neuromorphic systems. There are other neuromorphic platforms out there. At present, SpiNNaker offers the world's largest neuromorphic platform, in the sense it's capable of supporting larger real-time biological neural network models than any other neuromorphic platform. And it offers advantages in terms of flexibility, but other platforms have advantages in other directions. And the jury is still out as to which is the optimal approach to build systems to model the brain. And so it's valid that there are all these different approaches, and maybe time will tell, or maybe it'll become clear that SpiNNaker is the best platform for this line of research, and the Heidelberg Brain Scales machine is the best platform for that line, and Loihi also has its strengths in another direction. I mean, it's the nature of research that you can't predict the outcome when you start. If you could, you wouldn't need to do the research.
Yes, absolutely. I hear you on that, because each of these chips that are being developed, the neuromorphic computing chips, each of them has its own strengths and weaknesses. Each one runs on a different platform. Each one has different system requirements and capabilities. So we will have to see, which one emerges as to be the more suitable one for further development, on which more applications can develop. But again, the development is not all going to center around one chip. It is going to be many chips will be used for many different kind of application development, different kind of system development. So we just have to make sure that they all can speak to each other, they all can integrate and interoperable, and that the system requirements are designed and defined in such a way that we don't create complex challenges integrating all of that. So each of these chips are going to be useful for solving the complex challenges facing humanity. So thank you so much, Professor Furber, for participating in this roundup today. We appreciate your thoughtful insight on SpiNNaker and the future of systems on a chip, and our global viewers and listeners will benefit tremendously from the information you provided today. So even if a single decision maker is able to understand the benefit or the potential of the neuromorphic computing model that is emerging after listening to this discussion, this risk roundup dialogue that we just had today, this risk roundup dialogue has been of service, and we thank you for that.
Okay, you're welcome.
Wonderful. So Risk Roundup, a global initiative launched by Risk Group, is a security risk reporting for risk emerging from existing and emerging technologies, technology convergence, and transformation happening across cyberspace, geospace, and space. We at Risk Group believe that risk management, security, and peace, they walk together hand in hand. Though security is related to management of threats and peace to the management of conflict, risk management is related to management of security vulnerabilities as well as management of conflict. And it is not possible to conceive any one of the three without the existence of the other two. All three concepts feed into each other. We believe that the security we build for ourselves is precarious and uncertain until it is secured for everyone across nations. Tradition becomes our security, so if we build a culture of managing risk effectively, it will lead us to security, and security will lead us to peace. Let's manage the existing and emerging risks together. For more information on the Risk Roundups, to watch the Risk Roundup webcast or hear the Risk Roundup podcast, please go to riskgroupllc.com and do not forget to subscribe and share. Until next time, I'm Jayashree, host of Risk Roundup, signing off. See you next time. Thank you.